안녕하십니까. 올쇼TV 시청자 여러분. 오늘도 저희 로데 슈바르즈 코리아에서 준비한 웨비나에 참석해 주셔서 정말 고맙습니다. 오늘 저희 준비한 웨비나는 UWB에 대한 내용으로 저희 준비했습니다. 저는 오늘 진행을 맡은 로데 슈바르즈 코리아의 최지홍입니다. 오늘 진행을 위해서 저희 기술지원팀에서 근무하고 있는 필드 애플리케이션 엔지니어인 이성우 매니저 자리에 함께 해주셨습니다. 이성우 매니저님 인사해 주시죠.
네, 안녕하십니까. 저는 로데 슈바르즈 코리아에서 기술 지원을 담당하고 있는 이성훈입니다.
예, 오늘 준비한 내용은 말씀드렸던 것처럼 UWB 기술에 대한 내용입니다. UWB 기술 요즘에 흔히들 또 많이 들어보셨을 것 같기도 하고요. 또 최근에 참 많이 들어보게 되는 각광을 받고 있는 기술인 것 같습니다. 오늘 그 자리에 함께 해주셨는데요. UWB 기술이 어떤 쪽에서 주로 많이 쓰여지고 있는지 이런 부분 간단하게 소개 한번 해주실 수 있을까요?
네, UWB는 울트라 와이드 밴드라고 해서 기본적으로 500메가 대역폭을 가지고 있는 펄스 신호를 사용하는 테크놀로지입니다. 기본적으로 최근에는 이제 그 모바일 폰에서 많이 적용이 되고 있고, 그 외에도 차량 키에 이제 디지털 키 서비스를 지원하기 위해서 차량용 이제 키를 지원하는 쪽에서도 많이 사용이 되고 있습니다.
그러면 주로 우리가 많이 쓰고 있는 스마트폰이나 차량 키리스 엔트리라고 보통 부르게 되는
네.
스마트 키 쪽을 말씀을 하시는 거죠?
네.
예. 오늘 준비된 내용 저희 독일 본사에서 글로벌 웨비나로 진행을 했던 내용을 저희가 국내 내용에 맞춰서 자막으로 처리해서 여러분께 준비를 했습니다. 그래서 오늘 내용들을 쭉 보실 텐데요. 생각보다 약간 깁니다. 그래서 오늘 지체하지 않고 바로 이어서 시작을 하도록 하겠습니다. 지금부터 준비된 내용 함께 보시겠습니다.
Hello and welcome to the Rohde & Schwarz webinar about a seamless ultra-wideband experience. My name is Jörg Köpp. I'm the host for today's webinar and I'm Market Segment Manager at Rohde & Schwarz for non-cellular technology and IoT technologies. When we are talking about ultra-wideband, then we can say there are essentially four cornerstones. One is about pulse radio. It is about low-power wideband, if you look more on the technology. Just two cornerstones. And to others, if you're looking more on the application space, it's about accurate positioning and secure ranging, which is a kind of new feature in ultra-wideband. If you are talking about seamless ultra-wideband experience, and I think that's one of the most important features for any technology, it's nice that you have a nice technology, but finally, it really depends how the user experience this and how they would like to use this kind of technology. Therefore, one of the most important things is the need for interoperability and quality of experience. We would like to talk about this. This is our main topic for today. This goes in line with some information about the continuous evolution of standards and regulation. Especially on the end, we will also look a little bit on the next generation ultra-wideband. And we will especially focus on the ongoing efforts in setting a certification framework, which is also kind of conditions for this kind of interoperability. We will have a dedicated look on FIRA consortium activities and also on the car connectivity consortium. And finally, we see more and more demand for over-the-air testing if you would like to achieve the required accuracy, security, and so on and so far. And therefore, we would like to have a look on this. I'm quite happy that I have not to explain this alone. I'm very proud that we have Mitch Kettrick from the FIRA consortium here with us. He will explain especially about the FIRA consortium certification process, about validated test tool, validated test labs, and so on. We worked together already, I would say, almost 2 years. Because, you know, Rohde & Schwarz is also a member of the FIRA consortium, so we are working in these working groups. And so I, at least once a week, in contact with Mitch and talk about, and I'm quite happy that he was willing to present here in our webinar. And moreover, we have Nicola, you know him also from other webinars as product manager for our non-signaling tester here for ultra-wideband, and he will show you some details and how you can really make the measurements in a pre-conformance measurements for ultra-wideband, probably conformance, and also the OTR measurements. But let's start with a short warm-up about ultra-wideband. If you look on the ecosystem, on the applications, then I can say what are the applications that I'm using today. This is keyless entry. I'm actually not using this with ultra wideband because it's quite new, but I think everyone is using this, just pressing the button and opens the door. Or asset finding, I use ultra wideband to find my keys and also my pocket. Some more advanced applications which are already on the horizon are, for example, secure payment, where we very often use NFC today. In the future, probably ultra wideband. Some nice applications about augmented reality and virtual reality, and also really the communication between ultra wideband devices, peer-to-peer communication, sharing content, and so on. If you look on the ecosystem, then you should be aware about a couple of organizations which are driving this, sometimes also driving this together. There's, first of all, the Ultra Wideband Alliance, which is a general, I would say, industry consortium driving ultra wideband technology in all different flavors. Then I mentioned we are a member of the FIRA consortium, which is especially looking on applications for secure ranging. I will come to this later. There's a quite new organization which is called Omlox, which is going more in the direction of industry applications for positioning and location services. And we have the Car Connectivity Consortium, which is looking on several different things around the car and the smartphones, but also adapting ultra wideband. And we are also member here as adopter member, Rohde & Schwarz. If you look on the market forecast for ultra wideband, and I was taking here a forecast from ABI Research, then we can see that already in this year, 2020, 500 million units will be sold with ultra wideband on board. And if you look more on the future, and especially the wide adaptation of smartphones will drive this, it is expected that in the year 2026 we will see 1 billion ultra wideband devices shipped in this year, not on air, shipped. If you look now a little bit more on the technologies, then we can start with the general definitions, which are quite old. I mean, in general, pulse radio, ultra wideband communication is a quite old technology, probably the beginning of radio communication. There are two definitions coming from US, one from DARPA, you know DARPA, all as an inventor of the internet, and the FCC, the regulatory body in North America, and especially in US. And they defined more or less what is ultra wideband based on the fractional bandwidth for this kind of technology. But essentially what I mentioned already in the beginning, it is all about very short pulses, 1 to 2 nanoseconds small in time, which generate on the end of the day a spectrum on the frequency domain which is quite wide. For example, what we're talking today in the range of 500 megahertz. And this brings me to the standardization of ultra wideband that we would like to address today, that is specified in the IEEE 802.15.4. Over the last couple of years. There's a couple of other technologies also related to this standard. So there's quite a big document. For example, if you look for Wi-SUN or for Zigbee, the related physical radio interfaces are also standardized there. But what we are looking in ultra wideband, there are essentially two areas. One is this high rate pulse repetition frequency, and the other is a low rate pulse repetition frequency. So there's essentially already two parts. We are focusing here on the high rate. And there is what I would call the legacy, which were already defined for a couple of years. This is for ranging devices. But what is new, and this is defined in the 802.15.4 set standard, which were published in 2020. You see here the related document. This is for enhanced ranging devices. And here we have a BPRF and a HPF. And the modulation is a pulse position modulation and BPSK, so binary phase shift keying with different pulse rates. This is more or less a standard rate. It's the same that you see here for the base or the legacy, and then you have higher pulse repetition rates. If you look quickly on the spectrum or the bands which are supported, for HRP there is a low band with one channel. There is something what is really called low band, 4 channels here, and then we have the high band, which is addressing most of the application. You see here also indicated which of these are related to FIRA. And for completeness, there's also this LRP, and this is only defined in the high band. If you are looking now how an ultra-wideband packet structure looks like and how the modulation, and I will just make this short, so probably that you just remember how it works. And I was taking here an example. This is HRP, Enhanced Ranging Devices, so means based on 802.15.4.z. So many letters. And it is an HRP, and it is a configuration SP2. I will come in a second what it means. So if you look on the packet, it starts normally with a kind of sync header, what you see here. Then there's an optional header, which is for security purposes, and then is more or less everything which is related to the data. The sync header is based on a ternary code, which is generated here, comes from the list. There are different lengths available. This code is then spreaded a bit by delta length, in this case here of 4. That means the minus goes to the minus, then 3 zeros, the next 0 goes to here. Then for the sync part, what you see here, there's a certain number of repetition, for example, 64 repetition of the sync code. For the frame end, what you see here, the SFD, they also take the symbols, the preamble symbols that you have here, and then the SFD sequence, and bringing this both together, have the SFD. For the STS, it's very similar. You have also here a sequence, the AES sequence, which is generated based on some keys and some initial values and so on and so far. Based on this, with some spreading, again, you get a kind of symbol, and then you take the symbol here in the STS sequence, also with some repetitions. If you look on the pulses, how this looks like, you see here you have pulses in one or the other direction based on the phase. And between the pulses, you have, in this case, for example, 3 0 pulses. That means you have a certain distance between the pulses. Fixed sequences based on these inputs. If you look on the header, then of course you have first of all the data header, which is a sequence with certain information. There's FCC coding, and then there's a convolutional encoder, which is the output 2 bits, and then they make the BPSK modulation. For the data, it's very similar. You have a bit stream of data, you have the red element code, then you have this convolutional encoding, and then the burst position modulation and BPSK modulation. How this looks like in the end of the day, for each of the 2 bits that you are getting out of the coder, you have 2 burst positions that you see here. One and the second burst. Between this, you have some kind of guard interval. And this has then a quite high rate. In this example, what I am showing here, HPF with this high pulse repetition, you have 1 pulse, 0 pulse, and the other pulse. So that's more or less the highest pulse repetition rate that you can have in an ultra-wideband packet. And this was very fast, but just to get an idea how this overall look like. If you look on test and measurement, there are the typical measurements which are defined in an IEEE specification. That's normally the transmission mass, some output power, and so on and so far. What is a little bit special, because this is a pulse interface, you have here this cross correlation magnitude, which says something about where is the main energy of the pulse located. And then there's also something about the pulse shape, which is related to this. So this just shortly to this stuff. Now I would like to have a little bit deeper look on what is FIRA-Dioden. The FIRA consortium has a kind of vision to interact with the environment by enabling precise location awareness for people and devices. That's very bold statements. So they would like to enable the ecosystem by defining and developing certain use cases, and also specify how the different functional blocks should work with each other and ensure the related interoperability. You see on the left-hand side how the overall architecture looks like, and where you see FIRA is heavily involved. I will not go in the details. There's a lot of specs and working groups in FIRA looking on this, looking on the use cases. And at the beginning, it was really focused on location awareness. In the meantime, in the discussion about the use cases, we see also some other use cases like peer-to-peer communication or car-to-car communication and something like this. For us, for the physical layer, what we are focusing on This is more or less the interoperability of the ultra-wideband system, essentially here on the RF interface. And for this, the interoperability on the RF interface is important, and also this UCI interface, which is a common interface where we control also the testing, so that every FIRA device which is certified can be used for the certification, this UCI interface. But this is just a short stuff. I would like to hand over now to Mitch. We have recorded his session because the actual situation, you know. And he will talk now much more about FIRA, the overall certification process, and especially on the physical layer certification. That is our main topic of today.
Hi, I'm Mitch Kettrick, and I'm the Certification Program Manager at the FIRA Consortium. The certification program is an essential element of FIRA's vision, where UWB-enabled smartphones from a variety of vendors can find location tags, securely unlock doors, and interact seamlessly with consumer electronics using FIRA-certified UWB technology from any vendor. Interoperability across vendors is a key element to the growth of any open technology ecosystem. The first phase of the FIRA certification program is aimed at driving interoperability between UWB devices. To enable effective testing of the baseline capabilities needed by devices, FIRA has built upon the IEEE standards 802.15.4 and the 4Z amendment by defining mechanisms that are beyond the scope of the IEEE standards. A device must pass all applicable MAC and PHY test cases to demonstrate that it conforms to the relevant FIRA specifications. This is a crucial foundational element in our drive for interoperability of UWB devices. But it's only the first step. In the future, FIRA will offer service certifications, which will require certification of the FIRA Common Services Management Layer and service profiles. This includes an application layer, which allows the discovery of UWB devices and services and configures them in an interoperable manner. FIRA has developed technical requirements available to FIRA members that describe UWB protocols to be used in MAC and PHY conformance testing. This includes verifying that transmitters meet minimum performance requirements. The test cases specified by FIRA are designed to verify hole shape and timing, packet format transmission, power spectral density, and overall signal quality. In addition, FIRA has also specified minimum performance requirements for receivers. This testing includes verifying successful reception of various packet formats, sensitivity, and dynamic range. Certification testing must be run on test platforms that have gone through FIRA's rigorous process of validation. This ensures that the test platforms comply with the test requirements defined by FIRA. The current list of FIRA-validated test platforms can be found on the FIRA website at the link shown. All FIRA-certified devices will be tested against these requirements by independent authorized test laboratories using the FIRA device certification process. These test labs must meet FIRA's requirements and pass an on-site assessment prior to being authorized to conduct FIRA certification testing. The current list of FIRA authorized test labs can be found on the FIRA website. In addition, we are in the process of authorizing additional test labs to provide testing services to FIRA members across the globe. FIRA has created a simple process for device certification. FIRA certification is only available to members of the FIRA Consortium. So, if you aren't already a member, Step 1 is to join FIRA. Step 2 is to review the requirements for FIRA certification and then to prepare for testing by providing key information about your device to the FIRA certification body and selecting a test lab from the list of FIRA authorized test labs. These test labs also provide pre-certification testing and debugging support if desired. Step 3 is to send your device to the chosen test lab for certification testing. The authorized test lab will execute the required certification testing using FIRA-validated test platforms. In Step 4, the test results will be provided to FIRA, and if the device passes, you will pay the device certification listing fee, and you will receive the certificate of conformance. Once the FIRA certification mark license agreement has been signed, you can use the FIRA certified logo on your device, packaging, website, or any other material. And, with your approval, FIRA will add your device to the list of certified devices on the FIRA website. To learn more about the FIRA certification process, including answers to frequently asked questions, please visit the FIRA website. If you cannot find the information you are looking for, you can contact me at the email address shown. In addition, you can learn more about the FIRA Consortium, what we have accomplished, and what is planned for the future by reading the 2021 annual report. Thanks, and I look forward to meeting you at future FIRA events.
Yeah, thank you very much, Mitch, for this comprehensive presentation about FIRA Consortium, and especially about the certification aspects. I think now for everyone is clear how this works and what you can expect from FIRA in this regards. I can just say, if you would like to have more information about, visit the FIRA Consortium webpage. There's a lot of information about this. Also some nice videos about use cases and so on and so far. Otherwise, you can also contact FIRA every time or also contact us. We have also the link to FIRA. As I said, we are a member and working closely with Mitch together in case of question to any certification stuff or in general ultra-wideband. But now we have heard a lot about the theory and how this works and should work. We would like to show you now, and especially my colleague Nico Serra, who is product manager for this nice product, how you can perform this kind of testing, pre-conformance testing or also conformance testing of ultra-wideband devices. And with this, I would like to hand over to him.
Thank you, Jörg. First, I would like to explain the hardware setup and software that is used in device verification based on the FIRA physical layer test specification. Part of our first demo is the CMP200, which is connected via cable and D-splitter to an ultra-wideband FIRA device. Instrument and device are both connected to a remote PC with our new ultra-wideband non-signaling software, UWB PHY Test Suite, which will automate test plan procedures and control the DUT via the UCI interface. For the first demo, we will not use the shielding chamber. This will be part of the second demo. But the test could also be done over the air, but you would still need a cable for the UCI interface. Before we have a look at the demo, let me first explain the tester and software a little bit more into detail. The CMP200 consists of an analyzer and generator. The analyzer's frequency range goes from 4 to 20 GHz, and the range for the generator goes from 6 to 20 GHz. The instrument offers 3 different ports, which enables to run regression tests with several DUTs on one box. This instrument is perfectly suited for the band groups and channels which are mostly used in the ultra-wideband ecosystem. The generator can replay chipset-specific waveforms, continuous waveforms, or you can create together with our software WinIQ Sim 2 your own specific waveforms and replay them. Part of the setup is also our time-of-flight kit, which is the suitcase on the right side. It is designed to improve the measurement accuracy, especially for time of flight and angle of arrival. With this concept, we can avoid trigger errors and can reduce the group delay of the whole setup. Now let's come to the software. As a software, we will use the new Rohde & Schwarz program UWB PHY Test Suite. This software is tailored for ultra-wideband non-signaling R&D applications. The user interface has two graphical user interfaces. One is to run the test plans, and the other is for changing parameters in a test case or deleting, adding new test cases to a test plan. There will be two different versions of this program. One conformance version and one pre-conformance version. The conformance version is limited just to the test runner GUI. You can only execute the fixed conformance test plan and get a signatured report. In the pre-conformance mode, you have access also to the test plan editor. Let me demonstrate the pre-conformance mode before it gets too abstract. On the left side, we see the test plan editor graphical user interface, and on the right side, we see the runner. First, let's have a look at the test plan editor. I will now load in the FIRA test cases. As we can see, there are plenty of them. I can click on each test case, and on the right side, we can see all the parameters defined in this test case. And these are also changeable. So you can really choose one test case to work on and really change different parameters. But for the demonstration, we will just delete most of the test cases, because as you can see, there are plenty of them and it would take some time to run them through. So we have now one test case here. Now I would like to add another FIRA test case, a custom one. So at the left bottom corner of the graphical user interface, we have a drop-down menu. We can choose if we want to add ultra-wideband FIRA test cases or normal ultra-wideband test cases. With this tool, it's not only focusing on the FIRA test cases, but also on all the other consortiums or regulatory test cases, such as FCC or IEEE. First, we will stay with the FIRA and we will add one test case, and we will choose the 1.5 chapter. So this is the one with the NRMSE measurements. And then we want also to test maybe for, let's say, power, modulation, and demask. So these are very important test cases which every DUT has to fulfill. So we will choose this. We will save it. And now let's have a look at the runner. So the runner is now doing our test plan. The first one went already through. Also our custom ultra-wideband FIRA test case was successful, and also the modulation, power and mask measurements. In the tab DUT1, we can have a look at all the different results. So the first test case, let's say it's a little bit boring. It's just to check the packet format. We can see that we have here a pass. For the PCT 1.5 test case, we can see what we have measured for NRMSE SHR, PHR and PCDU. So we have here the values, and we have here also the maximum allowed threshold. So if we would have measured something above this, then it would be a fail, not a pass. And here we have in addition the measurements for modulation, power and demask. So we can have a look at the frequency error, the chip clock error, the side low peak, symbol modulation, accuracy, chip time, jitter RMS, chip phase jitter RMS, and so on. Now we can also have a look at the maximum spectral density power. So we have measured a value minus 43.52 dBm per megahertz. And as we can see, it's a pass because we are under the threshold. These test cases are specified to be conducted, but it would also be possible to run them also over the air. To make it clear, the specification is only conducted in FIRA, but this is just a possibility to run them also over the air. In fact, ultra-wideband is a technology which should be tested mostly over the air, because the two algorithms which are used for the positioning applications, time of flight and angle of arrival, are heavily influenced by the used antennas. Jörg, could you maybe explain us a little bit more in detail what are these algorithms, time of flight and angle of arrival, all about?
Yeah, thank you very much, Nico, first of all, for this nice demo. Yeah, let's have a deeper look on this kind of technologies or techniques, which are one of the main topics in ultra-wideband today. As I mentioned, in the future, we will probably also see some other applications which are not directly related to this ranging and location stuff. But worthwhile to start with the point, what is the main idea in measuring location or distance or proximity or however you'd like to call it. Now, I would like to start with a quick overview with the most famous technologies that, interestingly, we have all on our smartphones today, all together. And we have now in addition also ultra-wideband, and what kind of techniques they are using to make this kind of estimations. What is already available, and probably also come then to the point, what is the big advantage for ultra-wideband, why going in this direction. I would not like to show you the typical slides with this is the range, this is accuracy, and so on and so far, because I think that always depends a little bit also from the applications, and I would like not to join this kind of game and blaming one or the other technology. Just very neutral looking what kind of principles they are using. Let me start first with Bluetooth Low Energy. And if you look on Bluetooth or Bluetooth Low Energy, of course, at the beginning in Bluetooth 4.0, they added features like for proximity and also Find Me. Probably some of you has also used Bluetooth technology to find a key and something like this. I had this some years ago. And this was really just relying on the received signal strength. And you know, in Corona times now, we very much people are also using this kind of Warn app and COVID apps, which are also using on the phones this kind of technology. And there's always a kind of accuracy stuff, but you can at least say, are you in proximity of someone? So this is based on the received signal strength. But of course, received signal strengths are really dependent whether you have line of sight, what is between, which conditions do you have your smartphone in front of you in the hand, or is it somewhere in your pocket? All this has influence on the received signal strength. Therefore, let's say that's not so accurate. In the next step, also Bluetooth Low Energy was going in the direction signal strength is one thing, but the signal propagation time is another thing. And signal propagation time you can also translate to phase differences, because if you have different signal propagation time from one sending antenna to two receiving antennas, you have in the end of the day a different phase. And they are using this phase difference introduced in Bluetooth 5.1 for direction finding, angle of arrival, and angle of departure. These are the both features that we know today from Bluetooth. If you look on Wi-Fi, very well known also that it is used by a lot of internet applications. Just I'm logged in a certain Wi-Fi access point with a certain BSSI. There's a database, and I can say, okay, you are sitting somewhere in Munich in this street, and so on and so forth. Also, signal strengths we're using to make this more accurate. And just recently, in the last couple of years, they started also with measuring propagation time. Interestingly, very similar, like we see in ultra-wideband now, with round-trip measurements and also extending this, what they call now, fine time measurement. So also using the propagation time for location-based services. Then we have all the cellular technologies, and they, as you see here, using more or less everything. Also the cell ID, which means I'm logged in a certain base station. Then also signal strength. They are also looking, especially if you look on new radio, which means 5G, new applications like here. That they are using more and more of the stuff. You see location services are more and more important. Also here in time difference measurements, and also they had in LTE already this round trip time, and they make a new radio now also multi-RTT. By the way, there's a new white paper from Rohde und Schwarz which explains all these different technologies. And then we have, of course, GNSS, especially if you would like to have locations everywhere, which is basically based on time of flight measurements between your device and satellite, and you know this information and can then, with different measurements and the end of the day kind of time measurements, find your locations. There are also some additional things with high precise GNSS and so on. There's also a webinar about this. If you look now on ultra wideband, then we have different things. And I will come to this now, looking a little bit deeper. In an ultra wideband, they are focusing on signal propagation times. And I have tried to categorize this a little bit. There's on one side is one-way ranging, and on the other side is two-way ranging. In one-way ranging, you can take as this, as one is this angle of arrival. That means one device here, which is probably static. An advertiser is sending out a message, and the receiver, for example, a smartphone, has two different antennas and can then measure here between the both antennas what is the phase difference. Then they have specified, and this is also in discussion at FIRA, the uplink time difference of arrival and the downlink time difference of arrival. This is if you have a kind of anchor, which is a kind of time synchronized infrastructure, and you can make this kind of measurements by sending out by the tech in a related measurement, and then you can receive this on different end devices and measure here the time difference. And you can do this in a similar stuff in the other direction as well. Then we have this, what we call the two-way ranging, which is also specified in the IEEE specification. And here we have a single-sided. That means this is like round-trip time. One message in this direction, one message in the other direction. You always measure 2 times on the initiator and on the responder side. And based on some simple calculation, you can calculate the time of flight here, or the propagation time, and then you can estimate the distance. This has some drawbacks dependent on the accuracy of the clock on the both devices. Therefore, they have also, for more accurate estimations, introduced double-sided two-way ranging. What you see here, to make the same more or less 2 times, one direction, the other, and back, and have here overall 4 time measurements, and then you can measure this more accurate. So these are the main principles. You see always some flavors, let's say, of these different things, but all this is based on the signal propagation time. If you look, for example, and I mentioned this in the beginning, on the CCC, on the Car Connectivity Consortium, they have just published the Digital Key Release 3.0. And this is for hands-free, location-aware keyless access and location-aware features. It's essentially a combination of Bluetooth, ultra-wideband and NFC. And you see this on the right-hand side. If somebody comes, or the owner of the car comes close to the device, they connect via Bluetooth low energy and make a kind of welcome and initialization, also exchanging secure keys and something like this. If it gets closer, then it starts with ultra-wideband communication, and not only a point-to-point communication. You have several communication with the car, because in the car you have several anchors which are synchronized by the onboard computing platform. And with this, you can make this secure ranging. I can exactly say, okay, the person is now on the left-hand side or the right-hand side, and it's really close. This is a kind of secure. And then you have NFC. This is especially if you are not able to use Bluetooth and Wi-Fi, probably your battery is running out of service, then you can use NFC. That's the principle of the Car Connectivity Consortium. I mentioned already we are also member on this. They are actually working on the certification approach, but our assumption today is that they focus on the certification, of course, of the interworking Bluetooth, ultra-wideband with the applications, also with the servers where you have the credential, because you can not only say that the driver is allowed to have access to the car, you can, via the server, also to say, oh, my friend is coming here, via the servers, I give you access with your phone to my car. So something like this. This is, of course, of high interest for interoperability and testing. For the physical layer, what we are focusing on, our assumption at the moment is that similar like Bluetooth, where they rely on Bluetooth SIG, they will probably rely on FIRA physical layer certification. But let's see, the final documents are not yet out. And just quickly, to come to the antenna topic, to explain why this is important here, just a picture how this angle of arrival is working with the phase difference. You have from one antenna the identical signal, which is coming from here and here on the both antenna on your devices. Because of the slightly different propagation time of the signal for one or the other antenna, you have a kind of phase difference, and based on the wavelength of the signal and the antenna distance, you can, and the phase difference that you measure, you can then calculate this angle, which is this angle of arrival. And if you see this, you can recognize, okay, the function that it probably work, you can test in the conducted mode, like here, with the device as we showed for the certification. You can look whether the timing is correct, whether they measure everything correct, but that you really can say that your device is accurate can you only do if you have a look on the full device, including the antenna, including the feed line to the antenna, including probably things which is around your device, because all this has influence how accurate you can measure this. And this goes exactly to this point where we see over-the-air measurements more important. So the first point is really that you have to think about the antenna characteristics. They have a large influence how accurate you can measure. And there are some points like matching, efficiency, antenna gain, the directivity, the group delay, because all this is of course dependent also on the frequency. You see this here on the graphs, which is essentially the S11 parameter, which is about the matching and efficiency. We have measured here two different antennas, and if you just think about, you have this wide bands which are available for ultra wideband, and we have selected just channel 5 and channel 9, and this is already a challenge to find an antenna which probably works over this high bandwidth of 500 megahertz and over all the channels which are supported. You have really to look on this, whether an antenna is working worthwhile. And you have also to think about really the characteristics based on the frequency. For example, we show here the characteristic of the antenna gain. It's the same antenna, one measurement in channel 5 and the other in channel 9. They are slightly different. Looks not big on the first look, but it has, of course, impact how accurate you can measure your range or your phase difference. And then you have always to think, again, measuring something conducted with a chip is nice, or conducted with a device, which is probably also a challenge because you have no cable plug where you can attach your test equipment. There are a couple of characteristics of your device which are very important. For example, you have several antennas on this. Antenna coupling. You have the antenna feeding line. The ground plane, everyone knows, has a big impact. Also the housing of the device and something like this. You know this all, I will just repeat this, but you see it is very important to make also over-the-air measurements. And we have, of course, also recognized this. We have a lot of contact with our customers asking how we can do this. Are the solutions that we have today, for example, for Wi-Fi, Bluetooth, 5G, also appropriate for ultra-wideband? Do they need something special, and so on and so forth? We had a deep look on this, and we would like to present you some of the results that we have seen and make also some demo. And with this, I would like to hand over again to Nico to explain us a little bit what kind of experience we made, what challenges we saw, and how we have solved this.
Sure, thank you, Jörg. Of course, there are some challenges on the DUT side, but there are also quite a few challenges on the test setup for ultra-wideband. And today in this webinar, I will discuss two of the challenges in detail. To have a known and consistent group delay over the whole setup is one of the challenge. And what is the right distance criteria between our tester antenna and the DUT antenna is the second topic. But before I come to these topics, I want first to discuss the setup. Part of our setup is the CMP200, a splitter, and CMQ with a built-in 1-to-6 switch and 3 different antennas which will measure the -45, 0 and +45 degree angle. The DUT has 2 antennas to perform an angle of arrival measurement, as we have learned from Jörg. So the signal will go first to the splitter. This splitter plays a huge role in the setup because it improves the timing of our time-critical measurements, such as time of flight. With our concept, we do not need to trigger the measurement, resulting in no trigger error, and we are able to move the mathematical reference point from our tester to the splitter, resulting in a shorter group delay for the whole test setup. The 1 to 6 switch is mounted at the back of the CMQ. This switch is a mechanical switch, which means that the group delay for each path is similar. Don't worry about that, we have verified this fact. After this, we have the cable connections to the antenna. Although it is a small part of the setup, it's one of my favorites. We have created a new ultra-wideband antenna kit with cables where we can guarantee a cable length tolerance of just 0.5 millimeters between the different kits. This is important to assure the same group delay behavior between the 3 different paths. Conventional antenna kits have often 3 to 5 centimeter tolerance due to the fact that they are not tailored for the ultra-wideband use case. These cables then lead to our ultra-wideband antennas. We have learned from Jörg that the characteristics of the antenna are very important. The signal will leave the antenna from the phase center, which will move back and forth over the different frequencies, resulting in a different group delay behavior. We have analyzed the group delay behavior of our antennas. The phase center is somewhere inside of our antenna, of course, depending on the frequency, and the interesting path to the DUT starts then from here. If we would calculate the distance from the top or the bottom of our antenna, we would always make an error of about 3 to 6 centimeters, again, depending on the frequency. On the right side, we can see the simulations for our ultra-wideband antenna. At the x-axis, we have the frequency range in gigahertz. On the y-axis, we have the shiftment of the phase center in millimeter. So this is the red curve. And on the right side, we have the group delay of the antenna. So this is the blue curve. We have highlighted the 6.5 and 8 gigahertz because here is channel number 5 and channel number 9, which are mostly used by the market. As we can see, the group delay behavior between these two channels are nearly the same. So there are just a few picoseconds difference, which is absolutely negligible for the measurements. To test ultra-wideband devices over the air is a challenge for the test system. You need to know every group delay in detail of your setup and watch out for the parts in the signal path which might increase the error of the setup if not analyzed properly. Luckily, Rohde & Schwarz has products for every part. Hence, we can take the responsibility for the whole signal path. The best example is the already mentioned ultra-wideband antenna kit with the short cable tolerance in between them. Another important topic is the right choice of the shielding chamber, especially in production. It should be as small as possible, but big enough to make sure to guarantee a suited distance between the DUT antenna and our tester antenna. The most known distance criteria is the Fraunhofer criterion, which defines when the far field begins. The question is, do we need to strictly respect this, or could we go closer? The traditional Fraunhofer distance is 2 times the square of the antenna size divided through the wavelength and defines where the far field conditions start. This distance is very important if you plan to do 3D measurements of the characteristics of your antennas. But we have seen in many cases that if you are just interested in the main beam, then you do not need to respect it fully. In fact, there are some white papers regarding this topic, and for these kind of measurements, the Dirac distance seems to be the way to go for ultra-wideband. As you can see, here is the formula for this distance. On the next slide, we can see what is the difference for channel number 5 and channel number 9 with our antenna for the Fraunhofer distance against the Dirac distance. So our antenna has the size of 7 centimeters. And for channel number 5, we get a difference of about 7 centimeters. So the Fraunhofer distance would be 21 centimeter or about 21 centimeters, and the Dirac distance would be about 14 centimeters. For channel number 9, the difference is really huge. So here we have saved about 10 centimeters. So the Fraunhofer criterion would be 26 centimeters, and the Dirac distance would be about 16 centimeters. We have made a simulation out of it in CST Microwave Studio, and these are the results. So we have simulated over different distances the angle of arrival for channel number 5. On the right side, you can see the setup of the simulations. Here are our 3 antennas. And these 2 dots represent the antennas of the DUT. The upper picture has a distance of about 9 centimeters, and the bottom one has a distance of about 15 centimeters between the antennas. We talk here about the physical distance between the antennas and not from phase center to phase center. So actually the distance is about 4 centimeters larger. For channel number 5, the Dirac distance is 14 centimeters. Note how the results get worse with declining distance. At 9 centimeters distance, the error exceeds 2 degrees, both for plus and minus 45 degrees. And from 12 centimeters, the results are pretty stable under 1 degree. Of course, all these values and simulations are only valid with our equipment. This is the reason why we have released a new CMQ product which is suited for the ultra-wideband frequencies. At the moment, only band number 5 and 9 are important, but in future this could change. This CMQ was defined to cover the whole ultra-wideband frequency range. It offers also a shielding of 80 dB, which is very good, and allows a multi-antenna setup. We will showcase the demonstration with 3 antennas, but it could also fit more inside. Yeah, so we have learned about the theory, we have seen some simulations, and now the time is ready for the real deal, for the demonstration. So we are now having the setup with the CMP200 and the CMQ shielding box. The DUT is inside of it, so you can see here that the 3 antennas are on the top, and we will perform an angle of arrival and time of flight measurement for each of these antennas with the DUT inside. So I have already prepared a test plan. As you can see here, we make 3 time of flight measurements and then 3 angle of arrival measurements. Now let us start the test plan. So we are starting first with the time of flight measurements. They are running. Maybe you can hear the clicking also from the 1 to 6 switch. And here are the results. So we have a time of flight distance mean of 16 centimeter. 16 centimeter. For the other antennas, we have the distance also of 16 centimeters, as we can see. So this is also the target because we have it in a circle. Here we have also 16 centimeters. And for the angle of arrival, we can see for the minus 45 antenna, we have measured minus 47.42 degree angle. For the mid one, we have a minus 1.3 degree and for the right one, we have 45.81 degree. So testing over the air will be important for this technology because the behavior of the antenna is a big influencer of the outcome of the results, as we have explained through all the slides. Especially for companies which are doing and or consumer products, it is recommended to test over the air. As we have seen, Rohde & Schwarz has not only all the necessary products in the portfolio for the whole system, but also is the competence carrier when it comes to measure the right way over the air to assure that technology companies can develop and produce their devices with the highest possible quality. Ultra-wideband gets now to get more and more recognized as the third big non-cellular technology besides WLAN and Bluetooth. This means also that this technology will be improved over time. So, Jörg, what can we expect from ultra-wideband in the future?
Yeah, thank you very much, Nico. And I think it's not a surprise that the industry is already working on the next generation of ultra-wideband, and also there's something happen in regulation and also in all this industry organization. I will just give you a quick view on this based on what is actually happening in the study group 4AB. That's the next group working on next generation ultra-wideband. Of course, they are looking on alternative coding, preamble schemes, modulation schemes, and so on and so far. They are also looking on more spectrum, for example, going in the direction of 12 to 13 gigahertz. They would like to make some improvements in the accuracy, reliability, and so on. Some new use cases like sensing, what you see here, or also streaming, low latency communication, also some other network stuff, and so on. So there are a lot of happening. So stay tuned what we can expect in the future. And I will close now with a final look on our products, our solutions, and also more or less what we showed today. We had a look on applications and test applications for the development, for the integration. We had a few on conformance testing, especially on FIRA. And of course, you can use our solutions also for production. Today, we were focusing on the CMP200 and the ultra-wideband physical test suite and the related OTR, which was in this case the CMQ200HS. But we have also some other solutions. You can take a scope together with VSE software. You can generate signals with SMM. You can analyze with our analyzers, and we have specific boxes, chambers for production testing. Main message, we have everything what you need for testing your ultra-wideband chips, devices, applications, and so on and so forth. With this, I would just like to give you a hint that we have some material on our website, worthwhile to read, some papers like an ultra-wideband white paper, an application note, and also some former recorded webinars. Please stay tuned and probably go on our ultra-wideband webpage where you see the QR code here. With this, I would like to thank you very much, Mitch, from the FIRA Consortium for his presentation about certification, and of course, Nico for his presentation and his insights about OTA testing and also our pre-conformance conformance test solutions. With this, thank you very much. We are looking forward to your questions and your comments.
네, 지금까지 저희 준비한 그 웨비나 영상을 보셨습니다. UWB 컨소시엄이라든지 그 UWB 측정 솔루션, 그리고 특히 위치 측이라든지 이런 부분에 적용할 수 있는 다양한 그 AOA 측정과 같은 이런 내용들 함께 내용들을 보셨고요. FIRA 컨소시엄에 대한 내용까지 같이 보셨습니다. 이성호 매니저님, 오늘 진행됐던 내용들을 간단하게 정리 한번 좀 부탁드릴 수 있을까요?
네, UWB 시스템이 최근에 각광을 받게 된 이유는 센티미터 단위의 이제 측이 기술과 기존의 테크놀로지와 차별화되는 보안 기술 때문에 이 해당되는 기술이 이제 각광을 받게 되었습니다. 그래서 오늘 그 보여드린 영상에서 내용들도 그 TOF와 AOA 기능을 중점으로 한 측이 기술에 관한 설명이 대부분이었었고요. 그 기술을 사용해서 향후에는 또 다른 이제 적용 사례가 나올 수 있는 새로운 기능들이 지원이 될 수 있을 겁니다. 네, 그리고 오늘 소개해드린 이제 피라와 CCC에 관련되어 있는 컨소시엄, 두 개의 큰 UWB 컨소시엄에 관한 내용이 있었는데, 피라 컨소시엄과 CCC 같은 경우에 저희 로데 슈바르즈에서 그 각각에 있는 스페시피케이션을 모두 다 지원을 하고 있는 상황입니다.
예, 깔끔하게 정리 잘 해주셨습니다. 오늘 지금 저희 준비되었던 영상이 생각보다 좀 길었어요. 그래서 오늘 긴 시간을 또 Q&A라든지 이런 부분들을 말씀드리긴 좀 쉽지 않을 것 같고요. 오늘 쭉 보니까 또 마침 오늘 질문을 해주신 분이 또 거의 없으세요, 또. 그래서 아마 제 생각으로는 오늘 내용이 굉장히 좀 자세하게 말씀을 드렸던 부분들이다 보니까 또 의외로 또 내용들을 이해하시기가 좀 더 편하시지 않았을까 이렇게 생각을 하기도 합니다. 이게 중간에 보면은 이종우님께서 올려주신 질문이 하나 있어요. 그래서 이커머스 사이트나 물류 시스템 적용 등에 대해서 문의를 해주셨는데 이런 부분들은 사실 아직까지는 UWB 관련된 직접적인 어플리케이션이라고 보기는 좀 어려울 것 같고, 다만 물류 시스템이라든지 이런 부분들은 이게 UWB 기술 자체가 또 근거리 데이터 통신을 목적으로 만들어지다 보니까 추적이라든지 이런 부분에 써먹을 수 있지 않을까, 사용 가능하지 않을까라는 생각도 들긴 하는데 어떻게 보시나요?
네, 말씀하신 대로 이커머스 사이트 같은 경우는 특별히 지금 당장 UW 기술을 사용하기 위하기는 좀 힘들 것 같고요. 대신 물류 시스템은 좀 광범위하긴 하지만 기본적으로 물류 시스템은 이제 물류를 보관을 하고 있는 장소에 각각의 태그 위치를 지정을 해서 제품별로 태그 위치가 지정이 된다면 UWB를 사용을 해서 추기 기술, 센티미터 단위의 추기 기술을 사용을 해서 제품의 위치를 실내에서 손쉽게 찾거나 기존의 새로운 담당자에게 공유를 할 수가 있을 것 같습니다.
예. 모든 기술이 그렇겠지만 현재 예상해서 앞으로 어떤 기술이 어떻게 사용이 될지 예상하는 건 사실 쉽지는 않을 것 같습니다. 다만 사용 사례에 따라서 또 굉장히 다양한 어떤 예들이 또 나오지 않을까. 그리고 질문해 주신 물류 시스템이나 이런 부분들도 추후에 우리가 볼 수 있는 어떤 사용 사례가 될 수 있지 않을까, 그런 생각도 들기도 합니다. 예, 오늘 지금 4시가 됐네요. 저희 1시간 동안 준비해온 내용들 쭉 말씀을 드렸고요. 오늘 준비했던 저희 발표 내용과 자료에 대한 부분들은 추후에 저희 로데 슈바르즈 코리아 홈페이지를 통해서 또 여러분께 제공들을 해드릴 겁니다. 그래서 이 내용들은 또 저희 쪽에서 참석하신 분들께 따로 인폼을 드릴 예정이기 때문에 이런 내용들 참조해 주시면 좋을 것 같고요. 추후에 혹시 오늘 이 시간을 통해서 질문을 못 해주신 내용이 있으시다고 하시더라도 그런 경우에 저희 쪽으로 또 연락을 주시면 저희 쪽에서 관련된 내용으로 정리를 해서 답변을 드릴 수 있을 것 같습니다. 그래서 앞으로도 또 계속적으로 여러분과 함께 이어나가는 좋은 기회가 될 수 있도록 저희 또 내용들을 함께 준비를 하도록 하겠습니다. 네, 오늘 1시간 동안 여러분, 시청자 여러분들 함께 해주셨는데요. 다음번에 또 저희는 다른 주제로 또 더 재미있는 흥미로운 주제를 가지고 여러분들을 찾아뵙도록 하겠습니다. 오늘 긴 시간 동안 함께 해주신 여러분들께 다시 한번 감사드립니다. 수고하셨습니다.